Well, welcome everybody to the NCSA Colloquium. I'm very pleased today to have Anshu Dubey here to give a talk on well, I'll read the title, I won't read the title, but anyway, basically on the importance of software frameworks in supporting not only high-performance computing, but in the science activities. The most important aspect of that is producing science. And as you all know, we're thinking a lot about how to organize NCSA in a way that can better support software as a really critical part of the cyber ecosystem, not only here at NCSA, but nationally. And I think it's really critical. When I was at NSF, we recognized the importance of software, and there's now a Software Institutes program that I hope will be expanding over time. And the more we talk about that here, I think the better. So it's no one better, I think, to give us an overview of particular aspects, particularly around a project that's been extremely successful in astrophysics. Anshu received her PhD in computer science from Old Dominion University in 1993. And a little while after that, she joined the University of Chicago in the Astronomy and Astrophysics department as a research associate, and ultimately became one of the key drivers of the so-called Flash code, and you'll hear some about that today. And then over the years, also, Anshu was at Lawrence Berkeley National Lab, and then back now at Argonne National Lab in the Math and Computer Science Division as a computer scientist. So look forward to your talk. Thanks.
Thank you. So, good morning. And before I get started with the talk, I want to point out that many a times the domain scientists get maligned for not knowing how to do the software right. And in this room today, there is the original architect of the Flash code sitting right here, who is very much a domain scientist. So people just haven't met with, there's Paul right there, people just haven't met with the right kind of domain scientists who know how to do software as well. I wanted to mention that. So I've divided up my talk in 4 sections. First one is the Flash version history with focus on software engineering, which sort of correlates the state of the art in the software engineering practices and how it got adopted in Flash. And then I'll give an outline of Flash code architecture with the view to how making it extensible so that it started, even though it started out as an astrophysics code, at the moment there are 5 major domains that are getting supported by Flash. Those include cosmology, astrophysics, that's supernova astrophysics, the biomechanical systems using fluid structure interactions, combustion, and high energy density physics. And all of that was possible because the Flash code architecture realized the extensibility and made it possible for people to just keep adding capabilities, specific physics capabilities in order to extend the reach of the code. And then I'll talk about the workshops that we conducted under a conceptualization grant from NSF, where the focus was to identify the abstractions that are useful for taking the software to scientific software to future. And I have been thinking a lot about how to architect a code framework so that these abstractions can be leveraged within the framework. And the last section of the talk will give a brief overview of that possible approach in design. So Flash version history. Flash began as a part of, in the ASC, what was then called ASCII and now is called ASC, Alliance Center, where the delivery of a multi-physics code was a stated objective. And the intent was to develop one code that could be used for multiple applications. All the applications were in the class of thermonuclear runaways. What they needed was compressible reactive hydrodynamics and specialized equations of state, which may have varied for different applications, and the nuclear burning networks. Also, all of these applications had a wide range of scale, so it was realized right from the beginning that adaptive mesh refinement will be needed. And because of people like Paul and Mike Zingali and Jonathan Dorsey, it was decided right from the beginning that the code will be released publicly just as soon as it was in some state of maturity. And this went a long way towards the software engineering practices that came into being in the Flash code. So initial version of Flash was just a forced three-way marriage, I would say, between Prometheus, which was the compressible hydrodynamics, Paramesh, which was the adaptive mesh refinement, and other research codes for specialized equation of state and nuclear burning that were smashed into one code. The interesting thing is that Flash first version was released within 2 years of the center getting started. So it was off to a good beginning. At the time of first version of Flash coincided with a focused effort by the DOE and other agencies into research into the frameworks. So several frameworks like Cactus, Samurai, Puma, etc., were outcome of this. And this was available as a resource to the people who were developing Flash. Plus also, there was an earlier effort, I think, from Paul's group called Cosmos, which had this idea of using the directory structure for inheritance and composability, and this was brought into Flash. So what happens is, because the code base was initially in F77, and there were common blocks for data sharing all over the place, etc., even though it was decided that the code should go in the direction of being object-oriented, the language support wasn't there. So what happened was the Unix directory structure was basically utilized to fake the inheritance of the object-oriented programming. And the concept of alternative implementations was introduced, where one directory would have one specific implementation, another directory would have another implementation, and a configuration tool would put the appropriate versions of that implementation together. But the other challenges that were there and didn't quite get resolved in the first version for obvious reasons, because it was just too early in the cycle, was that there were inconsistent data structures, there were divergent coding practices, and there were no coding standards. Now, testing was introduced because there were multiple people contributing the code. They wanted not to sort of collide with each other, and so they were testing on a regular basis, but the testing process had not yet been formalized. Then came version 2, and the main thing that version 2 wanted to do, that transition was trying to do, was to inventory all the data there was and sort of generalize the data management in some way. So this version went what was popular at that time, which was the centralized databases. That artifact still exists in some of the frameworks from that time, for example, Samurai. So what they succeeded in doing was eliminating the common blocks. They differentiated between the different variable types that were there, and the object-oriented approach was more formalized. So the setup tool, initially it was, I think, Perl, and then it became Python and got much more formalized. And meta information about the config files. So config files were sort of ad hoc.
It was initially C shell, actually.
It was C shell. Oh, okay. That part I did not know. Okay. And so what was acceptable and what should be put in the config files was formalized more. The testing also got formalized. More regression tests were added, and the testing itself during the transition to Flash 2 got automated through a test suite tool, and the test suite started running on multiple platforms. There was an attempt to modularize, so the Fortran 90 modules, they may have been introduced, many of them were introduced in the first version itself, but Flash 2 sort of imposed this requirement to have the Fortran modules to define the unit of a code, and the documentation began formalized too. But there was still this problem that because of the centralized database, what happened was every functional unit had two branches of control. There was one branch one branch of inheritance that went for data, and the other branch of inheritance that went for the actual functionality of the code. It was very non-intuitive, and there were two things that happened. One was that it became non-intuitive, and the developer for a new developer to come in and become familiar with the code, that ramp-on time became much higher because it just was much more confusing to navigate the code. And the second one was, somehow or the other, this process of differentiation between code and data broke the IPA optimization, and this code ran about 20% slower than the Flash first version did. So it did not get widespread adoption within the center for a very long time. People just kept adding to Flash 1, which became a challenge. But then along came version 3, and this coincided with the time that in scientific codes community, people were beginning to pay attention to full software lifecycle and a formal software process. So the Flash 3 had this in mind, that we were really going to provide encapsulation within the units of the code, and we are going to really realize the extensibility of the code. So we kept the inheriting directory structure, configuration, and customization mechanisms from earlier versions, and I don't see them going away anywhere anytime soon, because they're really flexible and they really provide the functionality that we need for the code. The things that happened over and above all of this was that naming conventions were defined, which means that up until now you couldn't differentiate between what was an organizational directory as in it's meant to be used in Unix, and what was the namespace directory as it was implementing the inheritance within Flash. So we used naming conventions to differentiate between them so that it became easier to navigate the code. We differentiated between API and non-API functions in the unit. So there was a very well-defined naming convention, prefixes indicating the source and scope of data items. So this was trying to go in the direction of write a code that's readable in some sense without having to explicitly document everything. Though unlike the general software engineering practices, you really cannot do away with inline documentation in a scientific code quite as easily, because you also need to explain the mathematical complexity and the logic as a part of your inline documentation. But also, another important thing that happened was that the data ownership and scope was resolved. So instead of going to a central database or residing in a common block where no one really knew what the ownership was, here each unit got to control its own data and got to control access to its own data. And if it wanted to get data from any other unit, it actually had to query for it, with the exception of infrastructural units where performance dictated that the data be shared among the units. The other important thing was physics being physics. It doesn't always lend itself to encapsulation really well because it wants lateral interactions. And so we paid a great deal of attention to how to devise data structures so that these kinds of lateral independences could be sort of hidden and there could still be encapsulation in the code. And there is an example of that later when I talk about the Flash architecture of how we got around this particular problem. We introduced subunits and built-in unit test frameworks within the code so that testing became even more rigorous than it was before. And unit tests in the context of Flash don't mean the same thing as they do in general software practices. For Flash, a unit test is one which tests a specific functionality. It might be making use of some of the other parts of the code because you can't completely eliminate all the dependencies in a scientific software the way you can in some of the other software. But a unit test is where that particular functionality can be tested against either an analytical or semi-analytical solution, or the same solution calculated using some other mechanism, so that the correctness of the implementation is not just dependent upon what someone approved earlier, but it also depends upon it's one more step in making sure that the implementation is correct. And then there are the usual regression tests where someone runs a combined integrated test, looks at the code, and a domain expert will approve that as being right answer, and that becomes the benchmark for future testing. And then came version 4. So version 4 did not change the code architecture very much. It was mostly a capability and domain expansion exercise. So here what happened was we ran up against challenges in software process. So it is the software process that evolved. And one of those challenges was this thing that there were 4 different streams of production science, each one of which was still adding code. So they wanted a common code base, but they wanted to be able to add their own codes also. And some of that code needed to make its way back into the trunk, but at the same time, a lot of it was mutually exclusive to one another. And this was a huge problem because managing the code consistency across multiple production branches is the test, until we devised a policy, the test suite was broken most of the time. So a green is a successful test run, a yellow is a test run where we sort of know things that are broken but don't need immediate attention, and red is when the test suite is broken, and we had weeks of red. We just could not get to even a yellow because everyone was merging in, and they were merging in. So someone who's working on fluid structure interaction will run their tests on that specific aspect and break something in the HEDP branch, and it was a mess. So what we did was, and this is weird, we used SVN's trunk as the merge area and made one what we call, so we devised a mechanism by which a backward merge wouldn't happen directly into the development area. It would happen in the trunk. There was a merge schedule. Each group was told that they could merge on this specific day, and the test suite will only take care of their merges, and the rest of the groups would not do any merges if the test suite broke and it didn't get fixed. So this was an division of responsibility, et cetera, et cetera. But what I want to point out is which is the much more interesting experience in Flash's context has been the mechanisms for version transition. So in version transition from 1 to 2, it was a very firm belief that the control should be strictly with the scientists. And therefore, the development and the production branches needed to be synchronized at all times, and there was a need for a backward compatibility in the interfaces at all time. What this ended up doing was it did not permit deep changes that needed to happen because they would have broken large chunks of code for large periods of time. Hugely increased developer effort because whatever was added in the branch 2, it was architecturally substantially enough different that same change needed to be then incorporated into 1 also, so effort was almost double, and there was high barrier to entry for a new developer. And as I mentioned before, it did not get adopted for production in the center for more than 2 years. This lesson was internalized, and when we went to version transition from 2 to 3, at this point in time, the infrastructure, a decision was made to differentiate between infrastructure and physics. The infrastructure development was handed over to the developers who were not actively using the code for research. And sufficient time and resources were made available to design and prototype. So there was no attempt at backward compatibility, and there was no attempt to keep the development synchronized with the production. What happened was, for over a year and a half, we just worked on defining the APIs for the various units, had the null implementations for the various units, and focused on the grid unit, which manages the discretized mesh, and the all of the other infrastructural units, I/O, grid, et cetera, that basically control the infrastructure, and did not transition a single physics unit until the framework was deemed to be, and we introduced test suite into it, so we did not start transitioning any of the physics until the framework was deemed to be quite robust. And then we slowly transitioned physics over, taking one particular application at a time. And this process took another 6. So the first application that could run on that infrastructure became active within about 3 months of us having the framework in place. And then Center moved to production using Flash version 3 long before it was released to the public outside, because what had happened was whatever bugs had been reported, whatever deficiencies had been reported in the earlier versions of the code were actually fixed while building the framework in Flash 3. And as we were doing the transition, those bug fixes were getting incorporated, so the code was provably better, the Flash version 3. But there are two very important factors to remember. One is that the scientists had a production code. So they weren't breathing down the developer's neck that they had a deadline and they needed a running code, because they still had a code they were working with. And the second one was that developers had been around long enough that they had sort of internalized the vagaries of the code and they knew what they couldn't get away with getting rid of. And in early days it happened even though we sort of knew what we were doing in the early days, we would look at something, a feature that was making the code messy, and we'd say, let's get rid of it, and we would, and something would break. So we realized that that messiness was there for a reason, and that's because the physical world that Flash is trying to simulate is messy. So next I move on to the Flash code architecture. So the philosophy of Flash code architecture is to encode the logical separation of functional units into a framework. And this is the philosophy of Flash version 3 as it is now. Separate what is exposed from what is private to the module, define interfaces through which modules can interact with each other. So for the infrastructure support, we need AMR. Also uniform grid with replication, and that is because in the high energy density physics version of the code there is also radiation which does not require the same degree of resolution as the hydro does, and so it makes a lot more sense to sort of restrict up to a uniform grid and then run the implicit solves on that. But even at other times we found the ability to switch between AMR and uniform grid to be extremely useful, because what we could do was we could develop a physics on the uniform grid and isolate the complexity of developing the physics from having to deal with all of the mess of the infrastructure of the AMR as well. I/O and runtime parameters and a Lagrangian framework. Now I call it a Lagrangian framework because it started out as a just trace of particles, but then we realized that what this provided, if we did this right, was an ability to have a data structure over and above the discretized mesh, which had the freedom, which gave the data items a freedom to move around in the mesh while still being able to interact with the mesh. So, and we turned it into a generalized framework, and now it has been used for things that you wouldn't have thought of before, because this is the basis for a laser drive in Flash. Because what it does is it treats the particle as the head of the laser, and so as the laser goes around it just moves as a particle and does its absorption and so on. Solvers were basically needed for mixed hyperbolic elliptic systems, and there are some in parabolic equations too, but vast majority of Flash applications use hyperbolic and elliptic systems. And then there are 0D computations like equation of state and Bern. There is time stepping, active and tracer particles. We differentiate between classes of units. There are infrastructure units, there are physics units. So infrastructure units also include a basic solver. For example, a multigrid can be used by gravity, it can be used by pressure and incompressible Navier-Stokes and so on. So the base multigrid solver is the part of the infrastructure, whereas its use by a specific physics is a part of that specific physics unit. Then we have the monitoring units which log the process, and then there is the driver unit which is actually the time stepping mechanism of Flash. And you can have more than one time stepping mechanism. The simulation unit is the specialized one. The simulation unit is where you define your application, and this is where the configuration tool starts looking for what to grab from the source tree in order to configure an application. Simulation unit is where you also define what the variables are going to be, what the runtime parameters are going to be, but this also provides the customization mechanism. Because we use our own homegrown setup configuration, any piece of code, however small or however large, if you place it in the simulation unit, it replaces the corresponding code anywhere in the source tree. So you have a very elegant, simple mechanism by which you can customize large chunks of code. Oof, what did I do? You can customize large chunk of codes, or you can customize a very small piece of code, and all you have to do is have its customized implementation placed in the simulation unit. And also, this is where you can define the initial boundary conditions, etc., etc. The basic architecture unit is a unit, and the reason why I refer to it as unit instead of a module is because that confuses with Fortran module. So a flash is a unit, a Fortran has a module, and a flash unit typically does not use Fortran modules except for housing data. And what they do instead of using a module in order to do the making sure that there are well-defined interfaces is to use the interface definitions of Fortran and use them and include them in the actual implementation. So Flash, you never build a binary out of the entire source tree. What happens is you have different combinations of unit that are used for particular problem setups. So what a unit does is it publishes an API for other units use, and the unit itself can have subunits which encompass sub-functionality within a unit. The interactions between units are governed by the drivers, and not all subunits of an included unit need be included in all applications also. So this is a generic example of a unit hierarchy. At the top level, there is the unit API which has the stub implementations, which don't do anything. And this is the mechanism by which a configuration tool can simply pick or not pick a unit without having to change the driver, because if you don't pick a unit, you just get the stub implementations and nothing happens with that unit. And that unit then can have subunits. So here there are two subunits here, a main and something else. And this is where you also start to do the implementation of the API. And so now this particular subunit has three alternative implementations. And this is how the inheriting directory structure comes into being, is that whatever is common between all three of these implementations is placed here and is inherited by all three of them. Whatever is common between these two implementations is placed in here, and it is inherited by these ones. And the general behavior is that whatever is in the green region actually overrides everything else that came before that. So these ones inherit from above and can replace anything that they inherit that is not visible to anything above. And at the last level, we have the kernel, which is where the actual implementation sits. And this is where we also relax the architectural requirements, because this is where the third-party software can come in, which does not conform to Flash's coding standards, etc. Here is an example of a unit which shows most of these characteristics. So this is the grid unit, which manages the discretized mesh. It has at the time I made this slide, it had 4 subunits. I think it has more now. But so there is the unit which this is what for the basic Eulerian mesh that sits under grid. This is what manages all of the particles, the Lagrangian infrastructure interactions with the mesh. The solvers is where things like multipole and multigrid, etc., sit, the basic solvers. And BC is where the specialized boundary conditions that are generally used in many different physics are handled. And this is the one which is most often actually replaced by a customized implementation in a user code. So then within grid particles, we have 2 sections, because map to mesh is not always needed. Map to mesh is only needed when particles are operating in an active mode, which means that they're actually influencing the the evolution. Whereas grid move, which actually moves the Lagrangian data structures within the mesh, are needed by everything that is using particles. So that's why they have their own sub-units, so that this one can be turned off when you don't need it. And then inside that, there is a specific implementation for uniform grid for Paramesh. And then within Paramesh, we have 2 different versions. And actually, now there exist more than 2 versions of how you move the data. Similarly, grid main has a uniform grid and a Paramesh. Within that, there is Paramesh 2 and Paramesh 4, et cetera, et cetera. And I haven't shown the entire hierarchy because this is the largest and the most complicated unit within Flash. And then there is the thing that I mentioned, how do you manage the lateral interaction between units when you want to have encapsulation? And the best example of that is particles, because time integration of particles has nothing whatsoever to do with the mesh. But in order to do the time interaction, you have to pull the quantities from the mesh into the location of the particles. So the way it works is the driver calls initialization calls particles init, which in turn calls grid init. And we have done this by making the data structure for particles extremely simple. It's just a simple 2-dimensional array where one dimension identifies the particle and the other one takes care of the attributes that are associated with the particles. We don't have any more complex data structure, and so that passing this data structure within different units can simply be done by passing by reference. And it does. And if you provide the appropriate APIs between the 2 units, then you can have this interaction happen without violating the encapsulation in any way. So this problem is actually solved by moving the control back and forth between units and passing the data along by reference as and when you need the transition. So far, this is all that I'm going talking specifically about Flash. Are there any questions? Yes?
Do you have like a symbolic manipulator?
Oh, yes, you need to take the mic. Sorry.
Symbolic manipulator program that can output code specifically for Flash. It just because in the Cactus framework there's ability to do that, and it might be fun to just sort of take similar set of equations and just sort of output for one framework or another, and then just sort of compare their capabilities. You could almost automate that.
That would be a good idea, but no, it isn't there.
Do you have any metrics that you use to assess the effectiveness of the software or the users, or how metrics for number of users, or what are the standard metrics that you use for?
We do actually, and it's all so what we did was at one point in time we were required to find out the number of users we had, so we sent out a survey and analyzed that survey, and then one great idea that came out of that was we provided a publications page on the website where people who have used Flash can add their paper automatically without having to go through the center. And people realize that that's a useful thing to do because it increases their own citation, etc. So according to that right now, there are close to 1,000 papers that exist in that database, and we have a script that can then from that database compute the total authorship, and that range I think goes well above 1,200 or so at this point. And of course we keep the statistics of downloads and so on. So
at one point we'd actually discussed having the code whenever it's run email some details of the run to central place, and of course you can see how people reacting to Windows 10 doing something similar to that, but we never implemented that.
Yeah, a lot of the things don't end up becoming implemented, even though everyone likes the idea, just because it's simply not possible with the resources available. There is one more thing that actually exists, and I think someone keeps track of that statistic also, is that I think Sean Couch has hosted a place where you can have add-ons to Flash. which means that they are not part of the release, but somebody somewhere has used them along with Flash, and so at your own risk you can get those add-ons and work with Flash, and I think they have a pretty good usage too. Right, so I move on to the next section, and the next section is about future concerns and the SI2 workshops. So this part is about the Software Institute, full name for the Conceptualization Institute. It's Software Institute for Abstractions and Methodologies for HPC Simulation Codes and Future Architectures. And the objective was to conceptualize an institute that could serve future computational needs of science through simulations on HPC platforms. And the motivation for this came because we had organized a workshop in 2012 on, again funded by NSF, on community codes. And we had invited people from various communities who do make use of community code and have, therefore, by necessity, a somewhat well-designed code base to come and share their experiences. And what we noticed was that code after code representatives went up onto present their architecture, their software practices, and the details might have differed, but the practices were remarkably similar. And this has all happened in disjointed efforts everywhere that had not done any coordination with each other. And so it occurred to us that here we are facing another major transformation because of the changes in the hardware platforms, and we are again trying to go it individually, one by one, each group trying to find its own solutions, whereas there is a lot of commonality, and therefore it might be worthwhile to leverage each other's experience and come up with a much more common infrastructure and framework for doing this transition. So what we decided to do was have a series of workshops where people were drawn from diverse disciplines and backgrounds. The first workshop was more comprehensive, and it had mostly people from academia, but also some people from industry. But the focus of this one was to gather information about the state of the art in programming, modeling, and other abstractions research, and state of the art in the software engineering practices in community codes from various communities, and also to gather information about what was it that the code developers were most worried about going into future. The second workshop did the same for the industry, and the final workshop in the series was focusing on the mathematics and the solvers that were common to many applications and that needed to be taken along to the next generation. And what was important was that research and programming abstractions were present in all of these three workshops, so that people who needed to use these abstractions could talk to and get input from the people who were doing research in these abstractions. So the future concerns that came out was that it's become clear to almost everybody who's doing anything that uses more than a single physics and is doing a small prototype type of work, that the currently followed mode of software lifecycle is getting close to the end of its time. The business as usual is not going to get us or allow us to be able to use the next generation machines in any good way. In fact, that future is already upon us. At that time it was still future, but now it is upon us. And the complexity is actually growing on two orthogonal axes, which makes this problem doubly hard. In fact, probably more than doubly hard, because not only is the heterogeneity increasing in the hardware, and where the data movement is becoming more and more expensive, per processing unit, less memory, all of which the CSE software, that's computational science and engineering software, dislikes. But there is also this problem that as people are getting closer to, as more understanding is coming from science through simulations, people want greater fidelity in their simulations, and the greater fidelity does not just come with doing the same thing, increasing the resolution, etc. That doesn't buy you a whole lot. It comes from using more complex models, and adding more complex models increases the heterogeneity within the software as well. So you have two axes along with which the heterogeneity is increasing, and neither one of them at this point in time we know how to solve very well easily at all. So here we are faced with a situation where we really can do with some focused thinking and some collaboration among the wide communities, which is what this institute was trying to do. So, yeah, well, it scares me. It is enough to scare the most intrepid computational scientist. There's no longer anyone who will make the boast that we will change the code as the machine comes along, because you have to change the code every other day then, pretty much. Anyway, so we also know that the larger your code base is, the more time it is going to take in refactoring, because we have the Flash experience in front of us, if not several others, where we did 6 months of design discussions and prototype building, 1 year from the start before the framework was even ready to be tested, another half year before we could do the first production schedule with that code. So first 1.5 years, Flash 3 was not available for use by the scientists. And I mean, that's something that anybody who's trying to do a major refactoring of the code has to be aware of. And all this is true when we were not touching the compute kernels at all, because our target hardware abstract machine model was still the same as it had been for Flash 1 and Flash 2. Now, we are not only facing a situation where we have to change the infrastructure in order to include these abstractions, we also have to do abstraction lifting for the solvers, the compute kernels themselves, because we no longer have a uniform target for our sequential or the single PE performance, which was true before. So it's a bigger problem than ever before. But as I mentioned before, this worked because we still had a useful production grade code available for doing science. And even though the overlap of the new and old code was tricky, it was indispensable. And the reason why I point this out is that we are at best about 2 years away from having to use codes on these ultra heterogeneous platforms. And we have production codes that are working on the current generation of platforms now. But if we don't start to refactor the codes now, and this is already late in my opinion, but if we don't start refactoring the codes now, those machines will come, and only the simplest of the codes are going to be able to make use of them. Anything that those machines are designed for, the really complicated multiphysics problems that those machines can be solving, the codes won't be ready for them. And at this point in time, consensus is beginning to emerge about the abstractions that are most likely to be able to be ready and be able to deliver the kind of performance we need from them. So it's time to start thinking about incorporating them into frameworks. So the key findings of the workshops was, among the application developers, there was much more concern about node heterogeneity than scaling. So, and for very good reason, because that's where your compute kernel sits. If you have to change the compute kernel, that really means that much more of the code needs transformation. And it's not even clear that transforming once is going to be enough. It's like however many different types of architectures exist, you have to have a version of the code for each one of them. That's the current performance portability state of the art, is that everybody who wants, with a few boutique solutions here and there, with that exception, everybody that wants to be able to use, say, Titan and Mira both, has to have 2 versions of the code. We also found that academia was much more aware of the impending difficulties than industry. A lot of people still have this attitude that I am just computing on my own local cluster. Why do I need to worry about the disruption in hardware? Well, that disruption in hardware is coming even to your local cluster, so there's no hiding from it. And this is something that at that time, industry had not realized at all. I'm not sure that there is all that much more awareness in the industry even now. There are a few that are aware of the problem. The emergent useful abstractions that I think can go a long way towards solving this problem are hierarchical parallelism, which means things like tiling, asynchronous task-based runtime, and declarative specification of operators. And I'm not saying that they need to be in any one particular form of declaration. They can be domain-specific languages, they can be some sort of functional languages, they can be somewhere where you reason about your code in a functional way but don't actually write it in a functional way. But the truth of the matter is we write our codes in a much more imperative way than we need to. That's just because the way the current generation of high performance languages are, you have to direct everything you want them to do. Whereas as far as the compilers are concerned, the more freedom you give them, the more you constrain the semantics, the more freedom you give them to rearrange the calculation, the better they're able to optimize, and that way you can also target different architectures. So there are other ways in which the people are approaching this. For example, there is COCOS in Raja being done at the DOE labs, where the C++ templated metaprogramming is being used to make the description of your solvers more declarative than imperative. The problem, though, is you have to buy into C++, otherwise you don't get any benefit of it. And a number of codes, and many of the largest codes that are in production happen to be Fortran based, so that doesn't help very much. But what so far the state of the art is that people have been using these individual abstractions, incorporating them into their codes, getting some information about them, and many times it turns out that changes need to happen even to get one of the abstractions to work. But really, we won't get to the point where we need to get to without using more than one abstraction in the same code. And what happens when you have more than one abstraction in the code? There is no data out there right now. So nobody knows what to do in order to bring these multiple abstractions into the code. No, there is one exception. Uinta does have two abstractions working into it at the same time, and probably OP2 also, but they're very, very few. And they're also, the difference between those is that those codes started with having one of the abstractions already built in. So Uinta started with asynchronous runtime already built in, and OP2 was always using a domain-specific language as its basis for its solvers. So we really have no instance of an application code that did not have any of these abstractions, that incorporated more than one abstractions and found out what goes on with it. So that's another cautionary tale. But so I started thinking about basically at least in the context of AMR and Flash, how can you incorporate more than one abstraction into the code so you still maintain the separation of concern so that they don't collide with each other and don't compromise the performance too much. And here is what I have sort of come up with so far. So first, before I go and launch into that, I want to summarize the desirable features versus why those desirable features don't always work out well in scientific codes. So you want well-defined structures and modules, you want encapsulation of functionalities, you want to minimize data movement, you want to maximize locality and scalability, and you want to have portability. Not just portability, you also want to have performance portability. You're working in all of that against the constraints where you can't just take the algorithm, a numerical algorithm that lets you have all of these desirable features. You trying to model a phenomena, you want to be as accurate about it as possible. So the accuracy and the stability of numerics also matters. And what that ends up doing is different pieces of physics want different kinds of solvers. So you end up having multiple solvers with diverse requirements, and you end up having intertwined interactions among solvers. So in architecting scientific codes, it gets messy because instead of having a well-defined structure and modules, you can, if you try to have the same data layout, that may not be good for all the solvers. You have many corner cases, and usually, you know, this is typically true in people who are talking about, for example, the stencil DSLs, is that they'll take a Laplacian, or at best they'll take a stencil that is, say, 27 points, and they'll write they will demonstrate that they can optimize and work really well, but where it really breaks down is at the boundary conditions, at the corner cases, and there is no answer to that problem. And as I mentioned before, there are necessary lateral interactions which make encapsulation difficult. There is often a necessity for transposition of data, and the many solvers have very low arithmetic intensity, so the maximization of locality and scalability become challenging. Very often what ends up happening is that proximity of data, so that you don't have long-range communication, and work distribution come at cross purposes with each other. So you improve one and the other one goes bad. So how to solve these problems? The problems, one of the ways to think about designing a code is to differentiate between its physical view and its logical view. For example, a discretized mesh is a physical view. But if you take one subsection of the mesh and you surround it with halo cells, that is the logical view. Because as far as the solver is concerned, it can't differentiate between one section of the mesh versus the entire mesh. So that's the differentiation between logical and physical view. So this is where you start the design with. The current generation of codes, if you try to map to this kind of a viewpoint, is that you have the real view is that you have a whole domain with many operators. And you do so this schematic is color coded in terms of the different views. So this is the physical view, this is the logical view, and this is what optimizations can happen because of taking that logical view. So you take the whole domain, you do its spatial decomposition, and you do its functional decomposition. A functional decomposition is basically you apply operators one after another. You don't try to apply the operators separate. So the corresponding virtual view is you have domain sections as standalone computation unit, which is your cells with the surrounding ghost cells. And your functional decomposition is a virtual view, which is a collection of components. And more often than not, this collection of components is actually not very dependent upon each other. They can be ordered in any way you like, because this is just, you're taking the current state and you're applying different operators onto it. So as long as you apply the operators in the same order on all of the data items concerned, it doesn't matter which order you apply them in. In some it does matter, but by and large it doesn't. And so what ended up happening was, because we took this virtual view of domain sections, we were able to optimize memory access and compute at the level of the physical domain, whereas parallelization and scaling optimization could be done at the level of the spatial decomposition. So this allowed the separation of concerns between single PE optimization and parallelization optimization, also different functional optimization. So that view has to change, and now what happens is we add a few things, because now we need more abstractions. So we take the abstraction at the solver level. So this part stays. We take abstraction at the solver level, and this is where the declarative approach to writing your solver comes in. Then you take the code transformation. So your domain sections and the abstraction at solver level together can then use the code transformation techniques that will allow you to have one code and use it on multiple platforms. The collection of components lets you, so you can't do very fine-grained division of functions, because then you have the function overhead. What you really want is for the readability and composability, you want to have small functions, but then you want to be able to fuse functions in order to achieve optimization, which means this is where the computer science research comes in. Similarly, dynamic scheduling. So now what happens is, do I have one more? No. So now what is happening is we're doing parallel and scaling optimization using the dynamic scheduling. We're doing the virtual view of component is feeding into the memory access and compute optimization as well, and the code transformation is feeding in as well. So now there is a little bit more complex flow diagram for a function, an application to be structured in order to make use of, in order to design it with using abstractions. And because I'm running out of time, I'll quickly skip over some of these. But here is the example of a hierarchical decomposition, for example, is where in AMR anyway you have blocks. When you take a mesh, you divide it up into boxes. You don't want to make the boxes too small, because then as you make them smaller and smaller, your Halo cell starts to dominate, and your second auxiliary memory will become much more than your physical memory. But if you just apply the tiling abstraction, where you can have, for example, a logical division, which means that you don't do an in-place update. So your source and destination are different, so that the source can have overlapping division, whereas the destination has non-overlapping division. Now you can have just same memory you can apply shared memory access here, and you can completely do these tiles in parallel without having any sort of conflict. So each one can go to a different thread. Now, there is the tiling abstraction, tiling library, which gives 3 different kinds of tiles: the regional, the logical, and the separate tiles. So what can happen now is you can take a large box, call that a regional tile that maps to a coherence domain in a hierarchical chip, and then the tiles work, tiles handle the finer grained parallelism within the code. And asynchronous execution barriers are the easy way to reconcile dependencies. We really don't need the barriers if we think about our dependencies carefully. So putting it all together is we have the construct the operators in the form of appropriate abstractions, specify the part of the domain and the conditions under which the operators apply, instead of asking for it to be done in a certain way, allow for mixed mode parallelism, where parameters control the degree of tiling or other form of mixed mode parallelism. And the framework owns and forms the data containers. The physics do not. And smart iterators that are aware of mixed mode parallelism and therefore can handle the dependencies and iterating loops that give up control. So that's as simple in some cases, for example, in Flash, as giving up for do I equals 1 to whatever. Instead of that, if you do while and then you ask for the status of a block or a tile to be ready and you just do it, then under the hood you can be having a whole bunch of asynchronous machinery that's not going to get in the way of your, which would not require a significant change in the code. And all of these codes can be incorporated in Flash, I can guarantee, without making significant changes to the code, except for the solver abstraction, which is where every single kernel will have to be touched. But I don't see a way out of that. At some point in time, it has to be done. And with that, I come to an end of this talk. Here are some useful links. That's it.
Thanks. Just given it's a little tight for time, but we have plenty of time outside. If there's perhaps one question we would like to ask here, take a minute for that. I have one quick one that I want to ask, but then we'll have time outside here. So how much are you working with industry in this? Because there was a meeting in this room, which I found quite inspiring. Maybe you were here in like 2008 with a lot of industry partners, and the topic was basically software, and it led to the idea about software frameworks and fluid structure interactions were one of the key sort of test problems of interest to a lot of companies and so on. So how much do you work with companies in thinking through, is this framework or these approaches useful for them and so on?
So the answer to that is I was doing a lot of that about 2.5 years ago when the SI2 was active, because as I said, Merle was one of the PIs in there, and one of the workshops was entirely focused upon the requirements for them. Then I moved to Berkeley. And so now I'm trying to get that whole act together again and try to get involved with those people again.
Good. I think we could do a lot together on that.
Yeah.
Okay. Well, why don't we thank Anshu again, and we'll meet up out here. Thanks.
Thank you.